Donc, notre conférencier titulaire aujourd'hui, c'est Joost Wardenier. C'est notre nouveau postdoc Poitiers à l'IREX. Il a fait son bac à Leiden et ensuite fait son doctorat à l'Université d'Oxford. Donc, on est vraiment content de l'accueillir ici depuis septembre. Son français est surprenamment vraiment bon.
Pas assez pour la prestation.
C'est pas la présentation. Mais je me souviens quand on avait vu son profil de candidat, tout était très axé sur c'est un nouveau mot que j'ai lu, le 3D-ness des exoplanètes. Donc, c'est ça qu'il va nous présenter aujourd'hui, sa recherche.
Merci beaucoup. Yeah, hello, good morning, everyone. So yeah, my name is Joost. Oh, sorry, I'll just stand there so that the people in the Zoom can see me. Okay, yeah, now I'm visible, right? Okay, yeah. Today in this seminar, I'll cover some of the topics that I worked on during my PhD project back in Oxford, which was about exploring the 3D structure of these planets that we know as ultra-hot Jupiters using a technique known as high-resolution spectroscopy. So let's dive straight into it. Just words. Okay, just use the space bar. Got it. I think I'm good. Thanks. Ultra-hot Jupiters are the hottest exoplanets that we can observe in our galaxy. So they are gas giants the size of Jupiter, but they are situated in extremely close vicinity to their host stars. So typically they orbit their star in 1 or 2 days. And this also means that they are expected to be tidally locked, so having a permanent day side and a permanent night side. On the day side, the temperatures are enormous due to the strong irradiation by the star. So we expect molecules to be dissociated and metals can be ionized. But on the night side, the temperature is a lot lower, and this is where molecules can persist, and this is also where cloud formation can occur. And typically these clouds consist of stuff like iron or silicates, basically. Now, because of this strong irradiation difference between the day side and the night side, ultra-hot Jupiters also feature strong winds in the order of kilometers per second. And typically the wind pattern can be decomposed into 2 contributions. Firstly, there are the day to night winds that blow material from the day side to the night side of the planet. And then depending on the exact conditions in the atmosphere, you might also have a super rotating jet that goes around the equator. Why are we interested in studying ultra-hot Jupiters? Well, first of all, I guess they are the sort of low-hanging fruit when it comes to observations. Ultra-hot Jupiters are relatively easy to observe. They are favorable targets. These are their extended atmospheres, their high brightness in thermal emission, and also their orbits are relatively short. So this means that we can do transmission spectroscopy, emission spectroscopy, and phase curve studies as well. And another very appealing feature is that day sides are completely cloud-free, so all the chemical building blocks can be found in the gas phase. And this means that we can detect and constrain their abundances using spectroscopy, basically. So when we manage to constrain the abundances of different atoms and molecules in the atmosphere, we can say something about the ratios, the abundance ratios between different elements, like iron to oxygen or carbon to silicon. And these ratios tell us something about how the planet formed and how it migrated in the protoplanetary disk. Like characterizing the planet atmosphere, we also have a window into the formation history of the planet. But of course, there's one big caveat, which is what this talk is about, and that is the fact that ultra-hot Jupiters feature extreme spatial variations across their atmospheres. So in order to really understand what is going on, and in order to come up with precise measurements of the abundances in these atmospheres, we need to make sure that we understand how the 3D structure of these planets translates into the data that we see into the spectrum. A very powerful technique to study the atmospheres of exoplanets is high-resolution spectroscopy. And in this talk, I'll specifically focus on transmission observations, where we look at the absorption spectrum of the star as it passes in front of the planet. And at high spectral resolution, it's possible to resolve the individual absorption lines of atoms and molecules. So this is illustrated here in the right panel on this slide, where you can see the opacity profile of carbon monoxide. And you can see that at relatively low resolution, the opacity is a quite smooth function, but then as we keep increasing the wavelength resolution, you end up with all these different absorption peaks. And because the planet is moving with respect to the star, the planet lines undergo a Doppler shift during the transit. And this is also a very natural way to isolate the planet signal from the stellar signal, basically. And yeah, because the spectrum contains this unique spectral fingerprint for every different chemical species, high-resolution spectroscopy is also a very good way to detect different atoms and molecules in the atmospheres of exoplanets. Now, this all sounds very nice in theory, but in practice, the high-resolution spectrum of an ultra on Jupiter looks like this. And that is because if we spread the light out over a lot of different wavelength bins, over a lot of pixels on the detector, the signal-to-noise ratio that we get per pixel or per line is actually very low. So in order to recover the planet signal, what we need to do is perform a cross-correlation. So we basically multiply the data with a template that contains different absorption lines. We slide the template along the data, and then we multiply the template and the data with each other. And then when the data and the template happen to overlap, you get this nice peak in the cross-correlation function, basically. So yeah, this peak in the cross-correlation function tells you a few things. First of all, if the peak is there, it means that the absorption lines that were present in the template are also present in the planet spectrum, so it's a way to detect species. The position of the peak in the cross-correlation tells you something about the Doppler shift of the lines in the planet spectrum. And also the strength of the peak is directly related to the strength of the absorption lines in the planet spectrum. So these are the sort of quantities that we deal with. So yeah, one of the most well-known, I guess, high-resolution transmission observations is shown in this plot over here. So it's the iron absorption signal of the ultra Jupiter WASP-76b during the transit. And you can see here in this figure the value of the cross-correlation as a function of velocity shift on the horizontal axis, and then the time during the transit on the vertical axis. And you can see that the cross-correlation signal traces out a sort of diagonal trail in the map. And this is a direct consequence of the orbital motion of the planet, because at the start of the transit, the planet is coming towards us. So that results in a negative RV, but then in the second half of the transit, the planet is moving away from the observer. So you get a positive Doppler shift. Now, for those who look with a sharp eye, you can see that the iron absorption signal does not entirely coincide with the shift that you would expect just based on the orbit of the planet. And we can see this a bit better when we shift to the planet rest frame. So this is a frame that moves with the planet as it orbits the star. And you can clearly see that the Doppler shift of the iron absorption lines deviates from zero. And this is a signature of the 3D structure of the atmosphere, because as I mentioned previously, winds in the atmospheres of ultra Jupiter are also on the order of kilometers per second. And around the equator, the rotation of the planet also contributes to the Doppler shifts that we see. This is a very interesting observation. In the paper that presented this transit of WASP-76b, they also proposed a sort of toy model to understand how the signal comes about. And that's what I try to illustrate here on the right side of the slide. So these schematics that you see here show the equatorial plane of the planet. So we sort of take a slice through the equator of the planet, and this is what we see. And basically, the idea is that iron, or gaseous iron, which is responsible for the absorption, is sort of asymmetrically distributed over the day side of the planet. So at the start of the transit, the idea is that the stellar light rays only cross the morning terminator of the planet. On the morning terminator, the day-to-night winds are pointing towards the observer, but the rotation is pointing away. So we wind up with a Doppler shift of about zero, because the blue shift and the red shift cancel each other out. But then as the transit continues, the evening terminator comes into view. And on the evening terminator, both the day-to-night winds and the rotation point towards the observer. So we get an increasing blue shift with time. And then at some point during the transit, all the iron on the morning terminator has rotated out of view, so that we're only left with the contribution from the evening terminator, basically. And that's why the blue shift stays constant during the second half of the transit.
Why does it gap? Why we don't?
So that's the Doppler shadow of the star.
Oh, okay.
So there's a, yeah, that's a good question. So there's a part of the observation where the stellar lines and the planetary lines overlap. And yeah, you can't really disentangle them. So yeah, that's why there's a gap. So yeah, this cross-correlation map is a very good signal to noise. In general, in high-resolution observations, the trill doesn't stand out that clearly. So you have to do another step to actually recover the planet signal. So here we have an example of another cross-correlation map. I think this is also for iron, but in the Ultra Jupiter WASP 121b. So you can somewhat see the trill, but it's not very clear. So in order to make the signal stand out more, what we can do is we can add up the cross-correlation signal along the time axis, basically. So an approach you could take is just to sum the cross-correlation values across different trills with different slopes and different offsets. So if we pick a random trill, let's say we pick trill A, we only sum up noise, so we end up with a value of roughly 0. But if we happen to pick a trill that is close to the trill that corresponds to the planet orbit, we're actually building up the signal over time. And this leads to a so-called KP-physis map. So every trill over which we take the sum corresponds to a point in this KP-physis map, whereby the KP refers to the orbital velocity of the planet, and the physis is the system velocity of the star compared to the sun. And you can see clearly here that there is a peak around trill B, around the green trill. But something that you can also see here is that the position at which the peak pops up in this KP-physis map is which is the blue dashes, is slightly different from where you would expect the peak to be situated based on the orbital velocity and the system velocity of the star-planet system. So this is also a signature of the fact that the atmosphere is contributing to the observation. So yeah, this is a very colorful plot from Stefan's paper, where they detect a whole host of different chemical species, which is very interesting. But if you look at the individual KP-physis maps, you can see that essentially in every map, the peak of the signal, so the peak of the detection, is offset from where you would expect it to be based on the orbital parameters of the planet, which are indicated by the black cross. So yeah, this really shows that these 3D effects are ubiquitous, and they pop up in the detection of many different chemical species. So yeah, the rest of this talk, I've divided it into 4 parts. I'll try to go through them all, time permitting. So in the first bit, I would like to have a look at modeling high-resolution transmission spectra using a 3D radiative transfer code that I used during my PhD. And there, really, the goal is to try and understand the connection between the 3D structure of the atmosphere and the sort of features that you can see in the cross-correlation and the KP-physis map. Then we'll make things a bit more quantitative and look at performing retrievals on high-resolution data. The goal of a retrieval is really to do a model data comparison and to optimize the parameters of the model so that the difference between the model and the observation is minimized. And then in the last 2 bits, I would like to have a look at infrared spectroscopy and look at the absorption signatures of water and CO, which are 2 very important molecules in Ultra Jupiters as well. And then finally, I would like to present some observations from the Ultra Jupiter WASP 121b, where we look at this water and CO feature. And I'll try to make a little comparison between the data and the models. Okay, so let's go to the first part. So during my PhD, I used this 3-dimensional framework to map the 3D structure of an exoplanet onto its high-resolution spectrum. So this slide shows a little schematic overview of how the framework works. So we start with a global circulation model. This is a 3D code that can simulate the 3D climate of an Ultra Jupiter. Then we map the output of the global circulation model onto this sort of disco ball configuration. So it contains the pressures, temperatures, chemical abundances, wind speeds of the planet as a function of latitude, longitude, and altitude. Then we feed this disco ball into a Monte Carlo radiative transfer code. So the low spectral resolution version of this code was developed by Elsie Lee, who was a postdoc in Oxford when I was there. She's now in Bern. And then for my PhD, I adapted this code to be used for high resolution spectroscopy. So what the Monte Carlo does is it randomly fires photons at the planet atmosphere, basically. And then for every photon, we compute the optical depth along the line of sight, also accounting for the Doppler shifts to the opacities in every cell that are due to the wind speed and the rotation of the planet. Then in the end, we average over all the photons. We do this for many wavelengths, and then we obtain the transmission spectrum of the planet. And by basically playing this game for different observing angles, we can get the time-dependent spectrum of the planet over the course of the transit, basically, and then obtain a cross-correlation map or a KP-Physis map. So yeah, this slide gives a little impression of what the outputs of a global circulation model look like for ultra-hot Jupiters. I inflated the atmosphere a bit here for visualization purposes. Yeah, you can see here that the temperature structure in the equatorial plane. Of course, the day side is a lot hotter than the night side, but also the day side is more extended than the night side due to the higher temperature and also the lower mean molecular weight of the atmosphere. Because on the day side, we expect a lot of molecules to be dissociated. So we basically have more particles, which results in a lower mean molecular weight. So yeah, the atmosphere is more puffy, more extended on the day side. And then the other plots here show some of the spatial distributions that we expect for different atoms and molecules across the atmosphere. So iron, for instance, is very abundant on the day side of the planet, but we expect it to be condensed on the night side due to the lower temperatures. Water dissociates on the day side, but should be abundant on the night side. CO is a very interesting molecule because it has a very strong triple bond between the C atom and the O atom. So it doesn't really dissociate, it doesn't really condense. So the distribution throughout the atmosphere is uniform, which makes CO a very important molecule for the temperature structure of the planet, for example. OH is a product of the thermal dissociation of water, so we expect it to be present mainly on the day side. And then there's also TiO, which is an interesting molecule, but which I won't go into detail about today. So yeah, the first application of this like 3D framework that I used this 3D framework for was to try and reproduce the iron signature of WASP-76b. And from the toy model that we saw previously, we saw that there needs to be a big asymmetry between the morning terminator and the evening terminator of the planet to get this increase in blue shift during the transit. So I played around with a few 3D models, so a few GCM outputs where I sort of artificially created an asymmetry between the evening terminator of the planet and the morning terminator just by removing some iron or by playing around with the temperatures and the scale heights. And you can see here that as we go from a big asymmetry to a smaller asymmetry, the agreement between the model and the observation actually becomes less good. So for the asymmetric model, where iron is just removed from the morning limb of the planet, the observation and the model show the same qualitative behavior, where you get an increase in blue shift during the first half of the transit, and then a constant blue shift in the second half. The dashed lines, by the way, show the full width half maximum of the observation. So yeah, apart from there being, I guess, just a velocity shift, the model and the observation agree quite well. But then as we reduce the asymmetry, as we increase the amount of iron on the morning limb, or as we increase the temperature, the agreement becomes less well. So this illustrates that there needs to be a strong difference between the evening part and the morning part of the planet. I think there's still some discussions in the literature what actually causes the asymmetry. Is it really a difference between the iron abundances? Is it maybe clouds on the morning terminator that mute the absorption features of iron? It could also be that there's a scale height difference between the morning and the evening terminator. And of course, the scale height of the atmosphere directly sets the strength of the absorption lines. So yeah, it's interesting to see, I guess, how one observation sort of unleashes a whole suite of modeling studies. So let's go to part two. So this was really a sort of like qualitative comparison between the data and the model. But recently, Sid Gandhi from Leiden did a retrieval study where he really tried to infer the values of different parameters that underlay the observation, basically. So this was the setup of his retrieval model. So in a retrieval, what you try to do is you try to run many realizations of a sort of parameterized model. You then compare the model outputs to the data, and you try to optimize the parameters to get the best match between the model and the observation. But because the model needs to be run many times, the model has to be evaluated quickly. So it's a parametric model, which takes a few parameters and then outputs the spectrum. And what Sid basically did is he divided the terminator plane of the planet. So this is the plane of the planet that we get when we cut through the planet from north to south. He divided the terminator plane of the planet into two halves, an evening half and a morning half. And then for each of these two separate models, there are a few parameters that describe the state of the atmosphere. So there is an iron abundance, there's a few parameters describing the shape of the pressure temperature profile, and then a few parameters associated with clouds and hazes in the atmosphere that set the continuum absorption. And then, of course, because we're looking at high resolution data, there's also a few parameters that set the Doppler shift of the lines. So these shifts in delta Kp and delta Vcis, and also some parameter that sets the dispersion in the wave velocities that the observation probes. The motivation for dividing the terminator up into two separate parts can be seen in this slide, basically. So this is, these are slices of the planet as we basically cut through the atmosphere from north to south. And because the planet is tidally locked, it rotates quite substantially during the transit. So that means initially that at the start of the transit, on the evening terminator, we see the night side, but on the morning terminator, we tend to see more of the day side. And then as the transit progresses, the day side comes into view on the evening terminator, and the night side rotates into view on the morning terminator. So from these plots, you can see that it sort of makes intuitive sense to sort of split the atmosphere up into two halves and perform a retrieval where you optimize the parameters for the evening terminator and the morning terminator. What Sid also did was to basically divide the transit into two halves, performing a retrieval for the first half of the transit and the second half of the transit. And you can see that as the planet rotates during the transit, this actually means that you can retrieve the properties of the atmosphere in 4 different regions. So in the first half of the transit, we get information about the orange region and the purple region, and then as the planet rotates, in the second half of the transit, we get the information about the blue region and the red region, basically. The paper is quite technical. There's a lot of figures in it. So if you want to know more about how these 2D retrievals work, I would refer to the paper. But this plot shows one of the main results, which are the retrieved iron abundances in these different regions of the planet. So these are posterior distributions, which sort of illustrate the probability of having certain iron abundance. And then in the bottom panels here, you see the retrieved pressure temperature profiles. Now, as we saw from the cross-correlation plots earlier on, most of the signal during the transit is actually coming from the evening terminator. So this is also the reason, I think, why the iron abundance on the evening terminator is very well constrained. But then on the other side of the planet, where the signal is a bit weaker, you get these larger uncertainties in the retrieved abundances of iron. And what's additionally tricky in high resolution spectroscopy is that during the data reduction, you sort of remove the continuum of the spectrum. So if you have a spectrum, you can basically get the same outcome by increasing your iron abundance, but also increasing the altitude at which your clouds or continuum absorbers are situated, basically. So that causes some degeneracies and increased uncertainties in this part of the planet. But overall, it turned out that the 2D separated phase retrieval, so performing the retrieval on 2 halves of the transit and dividing the atmosphere into 2 different parts, that method was preferred by almost 9 sigma, or by almost 5 sigma over a modeling approach where you just represent the atmosphere as a one-dimensional atmosphere. And this really shows that high-resolution transmission observations can provide you insight in different regions of the planet and really allow you to spatially resolve what's going on in the planet atmosphere, which is very nice. So the paper also included a small comparison between the sort of best fit spectrum that I obtained with my 3D modeling framework and the best fit spectrum that SIT obtained from its 2D retrieval. And you can see that in the first half of the transit, the spectra actually agree very well, also in terms of line strength. Yeah, the 3D spectrum generated from the global circulation model contains more features. And this has to do with the fact that, in the 3D model, the photons encounter different temperatures, they encounter abundance gradients, different wind speeds as well. Whereas in the sort of pseudo 2D model, this is not the case. Then for the second half, the line shifts still agree quite well. But there's a bit of difference between the strengths of the absorption lines. And this could also be due to the fact that we're comparing a 2D model to a 3D model. So the 2D model was really optimized to fit the data as well as possible, and the 3D model was more a qualitative comparison to the data. But still it's interesting that these two different representations of the atmosphere give rise to roughly the same results. Okay, so flying through the talk, so I think I'll be able to do the the last two parts as well. Now we'll shift gears a bit from looking at iron in the optical regime to looking at water and carbon monoxide in the infrared. This was a paper that I worked on in the last year of my PhD. And basically the question that we asked is, given the distribution of a molecule in the atmosphere of an ultra Jupiter, what are the sort of regions that the absorption lines of that molecule probe in the atmosphere? We first looked at carbon monoxide, which, as I mentioned previously, is distributed quite uniformly across the atmosphere. And the question basically is, as this planet goes through the transit, what are the sort of regions that are probed? So what are the sort of regions that the spectrum contains physical information about? So that's what is shown in this plot over here. So these 5 individual panels, they basically show the morning terminator of the planet as we go through the transit basically. So the planet rotates, and this dashed line over here sort of marks the boundary between the day side of the planet and the night side of the planet. And then what I'm plotting here in the left panel is a CO absorption line that you would get if you only looked at the photons passing through the morning terminator of the planet. And then there's these colored regions here in the plots, and they basically show the regions that are probed by the continuum of the spectrum. So that is this line over here. And then the blue region is the absorption region that is probed by the line core of the CO line, basically. One interesting thing to notice is that even though CO is distributed uniformly across the atmosphere, the line core of CO pretty much always probes the day side throughout the entire transit. And here at the start of the transit, the line core probes the day side, but the continuum probes the night side. And this is because the continuum in this case is made up by water. And we can also see that as the transit continues, the sort of projected separation between these two absorption regions increases during the transit. And that also means for your line strength, that your line strength is going to increase during the transit, just because you get this geometric effect whereby the planet rotates and whereby the line core of the CO line starts to put up lower and lower pressures, basically. Of course, if we would play the same game for the evening terminator, we would see that the absorption signal would decrease during the transit, because we start with a big separation between the absorption regions, which then decreases during the transit. So what does this mean in terms of the cross-correlation map? So this panel here in the middle shows the cross-correlation map of the CO absorption feature when we only consider a planet with rotation. So we ignore the contribution from winds here. And you can see that the CO absorption feature clearly has two modes. We have a redshifted feature that corresponds to the morning terminator of the planet, and its strength decreases during the transit. But we also have a blue shifted feature, or a blue shifted mode, that is associated with the evening terminator, whose strength increases during the transit. And if you translate this cross-correlation map to a KP-physis map, then this is the sort of typical peak that you get. So the peak has a sort of triangular shape, which means that there's different combinations of KP and physis that fit the cross-correlation signal equally well. And you can see here in the cross-correlation map why that is, because if you sort of like try to find a straight line with a certain slope and a certain offset that fits the signal well, then you could fit just the red shifted mode, just the blue shifted mode, or you could maybe sum the signal along one diagonal line, which sort of fits both modes at the same time. But yeah, in this case, we also see that the shift along the KP axis is negative for carbon monoxide. Now we can do exactly the same for water. So the interesting thing with water is that water is depleted on the dayside due to dissociation of the molecule. What you can thus see here is that if we look at a transit at different stages, we can see that in the first part of the transit, the observation basically probes the night side of the planet. But then as the transit progresses, the region that is probed by the line cone of water sort of shifts to the day side of the planet. But on the day side, at lower pressures, there's no water, so the absorption region needs to shift to higher pressures. And effectively, the distance to the absorption region that is probed by the continuum of the spectrum decreases. So if we were to look at a water line associated with the morning terminator of the planet, we would see that the line strength decreases during the transit. So this is the exact opposite effect compared to CO. And this is really due to the spatial distribution of water across the atmosphere. Also for water, we can plot the cross-correlation signal basically. So now we also have a red-shifted mode and a blue-shifted mode associated with both terminators of the planet. But you can see that the behavior of their strength, or the phase dependence of their strength, is the exact opposite compared to CO. So if we plot the KP-physis map, you can see that we also get this triangular feature, but this time the offset is positive along the KP axis. This is quite interesting, I think, because it shows that if you look at the KP-physis map of a planet, you can actually say something about how the molecule is distributed across the atmosphere of the planet. In the paper, I'm exploring many more different atmospheric scenarios. I'm also looking at the signatures for iron and OH and TiO. So if you're interested in looking into these scenarios, then I would recommend reading the paper. Happy to chat to you about it as well. So then let's go to the last part of the talk, which is about transit observations of the ultra-hot Jupiter WASP 121b that we performed with IGRINS last year. So IGRINS is a high-resolution spectrograph from the Gemini South telescope. It targets the infrared between 1.4 and 2.4 micron. And this is also the wavelength range where we expect the spectral features of water and carbon monoxide to pop up. These are the KP-physis maps that we obtained. So this is real data from the telescope. These are the KP-physis maps that we get for the individual transits in the case of CO. And what's interesting to see is that in the individual transits, the peak position is not entirely the same. I think it is consistent though, because the block is quite extended in the vertical direction. But if we sum all these KP-physis maps together, if we combine the observations, we get a very clear signal of CO that is slightly offset in terms of its systemic velocity, which hints at blue shifting day to night winds on the transit during the transit, but also the offset in Kp is negative, which is consistent with the model that I just showed. So that's very nice to see. And these are the detection plots that we get for water. So yeah, in the individual transits, it's harder to recover water. The SNR barely gets above 4, and I think it's only when we combine the transits together that we get a clear detection peak. And in this case, you can see that there's a positive offset in the Kp parameter, which is also consistent with the fact that water is depleted on the day side, and that the observation that we see here is probing mostly the night side of the planet. And then I also, just like the whole, I think, goal of the initial observing proposal that I submitted was to really resolve the absorption trails of these molecules in the cross-correlation map. But as you can see in the infrared, it's quite a bit more tricky than doing it in the optical for iron, for example. So if we stack all the 3 transits together, this is the absorption trail that we get for CO in the stellar rest frame. And then if we translate it to the planetary rest frame, you can sort of see this faint vertical trail for the CO absorption. And then, for water, things are a bit more noisy. So if we combine the 3 transits, this is what we get. And then if we translate to the planet rest frame, you sort of see the water signal in the second half of the transit, but in the first half of the transit, it doesn't really pop up. So this also suggests that there's a really clear change in the strength of the water absorption lines during the transit, which I think might be due to water dissociation on the evening limb of the planet. Because something that I did was to basically sum up the cross-correlation signal in the first half of the transit, and also sum up the cross-correlation signal in the second half of the transit to get these 1D cross-correlation plots again. And what you can clearly see is that in the first half of the transit, the water signal is quite weak, but in the second half of the transit, it pops up quite strongly. And if we zoom in on these plots a bit more, then you can see that during the first half of the transit, the cross-correlation function is actually blue shifted, which hints that this contribution comes from the morning limb of the planet. But in the second half of the transit, the cross-correlation function is red shifted, which suggests that this contribution comes from the evening limb of the planet. And the fact that there's a strong difference between the line strengths in the spectrum apparently suggests that there is maybe less water on the morning limb of WASP-121b, which could be due to the thermal dissociation of water. But that's something I need to do more modeling for. Wait, I'm going the wrong way. Okay, so that brings me to the conclusion of the talk. We've seen that high resolution spectroscopy is a really powerful technique to study the 3D structure of ultra Jupiters, to say something about how different atoms and molecules are distributed across the atmosphere. Because of their different distributions, they also show different absorption signatures and cross-correlation map and in the Kp map. And also, if we look at the phase dependence and time dependence of the signal during the transit, this can provide some insight into differences between the evening terminator of the planet and the morning terminator. And I think the IGRINS observations might show evidence for water dissociation on one side of the planet, resulting in a weaker signal during one half of the transit. That was it. Thank you very much.